Hi students, welcome to the session of the subject Engineering Mathematics. Now in this session, we discuss characteristic equation definition followed by examples and characteristic values, that is eigenvalues, and few tips to find eigenvalues very easily, right? So this is characteristic equation. Suppose A is a n cross n matrix. Its characteristic equation is defined as determinant of A minus lambda I equal to 0. Now in this case, the lambda is some variable. This lambda is a variable quantity. And I is an identity matrix. I is identity matrix of size n cross n. So my matrix is A whose size is n cross n. Its characteristic equation is defined as det of A minus lambda I equal to 0. Now in this equation, lambda is some variable just like x and I is an identity matrix of size n cross n. Please write the definition. Let A be any n cross n matrix. Let A be any n cross n matrix. Full stop. Det of A minus lambda I equal to 0. Det of A minus lambda I equal to 0 is called characteristic equation of capital A. Det of A minus lambda I equal to 0 is called characteristic equation of capital A, where lambda is a variable, and I is an identity matrix of size n cross n, and I is an identity matrix of size n cross n. Now let us illustrate this definition by taking simple 2 by 2 matrix. Suppose I have a matrix A equal to 1, 2, 3, 4. Now this is a 2 by 2 matrix. So its characteristic equation is det of A minus lambda I equal to 0. This implies A is 1, 2, 3, 4 minus lambda I is lambda 0, 0 lambda equal to 0. This implies subtract lambdas only from diagonal elements. So this is det of 1 minus lambda 2, 3, 4 minus lambda equal to 0. Now this implies this is determinant of a 2 by 2 matrix. So this into this minus this into this. So this is the product 1 minus lambda into 4 minus lambda minus 2, 3, 6 equal to 0. Now this implies this expression is lambda square, right? This is lambda square. So minus lambda minus 4 lambda minus 5 lambda plus 4. 4 minus 6 minus 2. Therefore, this is nothing but characteristic equation of this particular matrix. So just take the example 1, 2, 3, 4. Apply the definition characteristic equation det of A minus lambda I equal to 0. Do the normal simplification. In this case, this is simply a determinant of 2 by 2 matrix. So that means we are subtracting lambda only from diagonal elements 1 and 4. And simplify the det value, we get an equation. That is lambda square minus 5 lambda minus 2 equal to 0. Therefore, this is nothing but characteristic equation of this matrix. Now, when you look at this equation, this is a polynomial expression. Generally, in the polynomial expression, we have variables followed by some constants. So, powers of variables followed by some constants. Now, it is in the form a into x square plus bx plus c equal to 0. Suppose if I assume that x is my variable, it resembles ax square plus bx plus c equal to 0. This is in the form ax square plus bx plus c equal to 0. Now this is a quadratic equation. Basically this is called a polynomial of degree 2 because the highest power of x is 2. That's why it is named as polynomial of degree 2. Basically in a polynomial, the polynomial expression, the quantities will be like this: powers of variables followed by some constants. See, in mathematics world we have exactly two types of equations: polynomials and non-polynomials. Polynomials means an equation which contains powers of variables followed by some constants. They will be called as polynomials. Suppose if I take x squared minus 4 equal to 0, it's a second degree equation. If I take sin x minus 4 equal to 0, this is not a polynomial expression. Let me write out. Suppose if I take this, ax square plus bx plus c equal to 0. Now this is a polynomial expression. Let me give one example. X square minus 9 equal to 0. In this expression we have powers of variable followed by some constants. And in this case the highest power of x is 2. So it is a second degree polynomial expression. Suppose if I take this expression sin x minus 4 equal to 0. This is not a polynomial expression. This is polynomial expression. This is non-polynomial expression. Right? Therefore, here why we are getting the highest power of lambda as 2, this 2 represents the size of this matrix. This 2 represents the size of this matrix. Therefore, the conclusion from this example is, when you define characteristic equation of a 2 by 2 matrix, you will get a polynomial of degree 2. If it is a 3 by 3 matrix, its characteristic equation is a polynomial of degree 3. In general, when you discuss characteristic equation of a n cross n matrix, it is simply a polynomial of degree n. Polynomial of degree n. Note down this example. Note, if A is a n cross n matrix, if A is a n cross n matrix, then its characteristic equation is a polynomial of degree n. If A is a n cross n matrix, then its characteristic equation is a polynomial of degree n. Now we discuss characteristic values or eigenvalues. Characteristic values or eigenvalues. This is the most important concept in linear algebra. Almost in 99% cases you can expect a question either from GATE or IES. Very standard model. Very standard model. So they may ask you what are the eigenvalues of this particular 3 by 3 matrix, or they may give you a 4 by 4 matrix. The largest eigenvalue of this matrix is, or they may give 3 by 3 matrix. The sum of eigenvalues of this matrix is, or they may give you one of its eigenvalue is given as, for example, 2. Then what could be one of its another eigenvalue? So let me recall the type of questions you may expect in characteristic values. I will define characteristic values within a short span of time, but before that you may expect many type of questions based on eigenvalues in GATE exam as well as IES examination, right? So they may ask you what is the smallest eigenvalue of a 2 by 2 matrix, what is the largest eigenvalue of a 3 by 3 matrix, like this, right? Now let us discuss the definition of characteristic values. Suppose A is a n cross n matrix. Now when you define its characteristic equation, it is in the form det of A minus lambda equal to 0. since this is a general value of n, when you simplify this equation resembles the form a0 into lambda power n plus a1 into lambda power n minus 1 plus a2 into lambda power n minus 2 plus and so on plus an equal to 0. Now basically this is a polynomial of degree n. This is a polynomial of degree n. Now when you solve this equation, we will get exactly n roots. And these n roots are nothing but the eigenvalues of this particular matrix. This is my n cross n matrix. Now let us define its characteristic equation in this model. Det of a minus lambda I equal to 0. Here I don't know what are the elements inside this matrix. Earlier when I started with a equal to 1, 2, 3, 4, I got the expression lambda square minus 5 lambda, for example minus 2 equal to 0. There I know the entries inside the matrix. Therefore I can able to say what are the coefficients of lambda square, what is the coefficient of lambda, what is a constant expression. But here I don't know the values of, I don't know the entries inside this matrix. So I cannot say what is the value of a0, a1, a2 as well as an. But there are certainly some real numbers. a0 is a real number, a1 is real number, a2 is real number, an is real number. Therefore, whenever you take a n cross n matrix, when you define its characteristic equation, it will be in this form. Basically, this is nothing but a polynomial expression of degree n. What is the advantage of polynomial? If it is a polynomial of degree n, when you solve this equation to get its roots, the number of roots will be exactly n. And these n roots are nothing but eigenvalues of the matrix A. These n roots are nothing but eigenvalues of the matrix A. Now, how to define characteristic values? The roots of characteristic equation of a matrix are called eigenvalues of A. The roots of characteristic equation of a square matrix A are called eigenvalues of A. Note this point. The roots of characteristic equation of a square matrix A are called eigenvalues of A. The roots of characteristic equation of a square matrix A are called eigenvalues of capital A. Note, if A is a n cross n matrix, then it has exactly n eigenvalues. If A is a n cross n matrix, then it has exactly n eigenvalues. Hope you understand this concept, right? Now let us work out on few examples. After that we discuss important shortcuts to find the eigenvalues of larger dimension matrices. If you ask me to find the eigenvalues of a 2 by 2 matrix, when I define its characteristic equation, you get a second degree polynomial expression a lambda square plus b lambda plus c equal to 0. Now even if you are unable to factorize a lambda square plus b lambda plus c equal to 0, we have a direct formula. So what is the formula to find the roots of a quadratic equation a lambda square plus b lambda plus c minus b plus or minus root over b square minus 4ac divided by 2a. But when you go to 3 by 3 matrix to find its eigenvalues, you get a third degree equation. There is no standard procedure to get the roots of a third degree equation. Then even if you go for larger dimension, for example 4 by 4, 5 by 5, etc., still the procedure becomes so complicated, right? So in that way, if you want to solve eigenvalues of larger dimension matrices, we have a few shortcuts. Let us discuss shortly. But before that, we discuss few examples to find the eigenvalues in a normal way, right? Suppose I have a matrix A equal to 2, 1, for example 4 minus 1. Suppose I have this matrix. Since it is a 2 by 2 matrix, I will get exactly 2 eigenvalues. So it has two eigenvalues. Now let us define its characteristic equation. This is det of a minus lambda I equal to 0. This implies that of subtract lambda only from diagonal elements. So 2 minus lambda 1, 4 minus 1 minus lambda equal to 0. This implies, so this into this is 2 minus lambda into minus 1 minus lambda minus 4 equal to 0. This implies 2 into minus 1 minus 2 minus 2 lambda plus lambda square minus 4 equal to 0. Now this implies this is lambda square minus lambda minus 6 equal to 0. Now this is my second degree equation. So what is my equation in this case? Lambda square minus lambda minus 6 equal to 0. Now this implies lambda minus 3 into lambda plus 2 equal to 0. So this is the factorization of this. Minus 3 plus 2 minus 1 minus 3 into 2 minus 6. Therefore, the values are like this. Lambda 1 equal to 3 and lambda 2 equal to minus 2. Now therefore, in this case, the eigenvalues are 3 and minus 2. The eigenvalues are 3 and minus 2. Right? Note this. Even without calculating this characteristic equation and solving for its roots, based on some trick or trick, I can tell you one of its eigenvalues. Even I will discuss maybe in the next session or maybe in this session. But for the time being, you can realize about this. You can see here this is first row. Add these two elements, you will get 3. 2 plus 1 is 3. Add these two elements, the sum is again 3. So in this case, sum of R1 means first row equal to 3. Sum of R2 equal to 3. Now this is a 2 by 2 matrix. When you add every element in row 1 and when you add every element in second row, we were getting 3. Therefore common sum, therefore 3 is one of its eigenvalues. Just now even we verified that 3 is one of its eigenvalues. The same logic works even for any n cross n matrix. Even if the sum of columns is same or sum of rows is same. So suppose I have a n cross n matrix. So sum of R1 is k, sum of R2 is k, sum of R3 is k, sum of Rn equal to k. K is any number. It can be 0, it can be fractional value also, it can be negative, it can be positive. Or sum of all columns is giving some uniform constant k. Then k will be one of its eigenvalues. Even I can prove that by using eigenvector concept. So when I go through eigenvector concept, I will give more clarification how we are getting this common sum as an eigenvalue. But for the time being, you can try to remember this. When you add all columns in any n cross n matrix, if you are getting constant sum, or when you add each and every element in each column, when you are getting uniform sum, that becomes one of its eigenvalue. This is very, very powerful shortcut to get the eigenvalue of any complicated matrix. Right? Even in 2017, for electronics and communication engineering students, one question was given based on eigenvalues. The size of the matrix is 5 by 5. The size of the matrix is 5 by 5. Interestingly, in each column there is exactly 1 1, exactly 1 2, exactly 1 3, exactly 1 4, exactly 1 5. So I have a 5 by 5 matrix. So 5 columns are there, 5 rows are there. In each column, so single 1, single 2, single 3, single 4, single 5 is there. So they asked, it has exactly one real eigenvalue, what it is. When you add 1, 2, 3, 4, 5, because in each column, single 1, single 2, single 3, single 4, single 5 is there. Positions have been interchanged. So even if positions have been interchanged, sum of column 1, sum of C2, sum of C3, sum of C4, sum of C5 is giving constant sum 15. 15 is 1 plus 2 plus 3 plus 4 plus 5. So 15 is one of its eigenvalue. Therefore, as I discussed in the last sessions, whenever the dimension of a matrix is complicated, if they ask you any question related to eigenvalues or rank or determinants or anything, certainly there will be some trick inside that. So try to understand elements inside rows or columns, you will get some magic, right? We discussed many shortcuts in this session, even maybe in the next session also, to get the eigenvalues of any n cross n matrix very easily, right? Now let me ask you one question. Suppose I have an upper triangular matrix or I have a lower triangular matrix. What will be the structure of its eigenvalues irrespective of size? I have a 4 by 4 matrix, right? I have a 4 by 4 matrix. Assume that this is an upper triangular matrix or lower triangular matrix. What will be the structure of its eigenvalues, right? Let us discuss an example. Suppose I have a matrix A equal to 2 0 0 0, 4 minus 1 0 0, 8 9 0 0, so 10 11, this is 12, for example this is, for example, 3. Suppose this is my matrix. Now let us see, here my diagonal elements are this. These are my diagonal elements. Here all elements above diagonal are 0. Now this is my lower triangular matrix. Now let us find its eigenvalues. When you define its characteristic equation, it is in the form det of a minus lambda I equal to 0. So this implies subtract lambda only from diagonal elements. Therefore, this is a determinant of 2 minus lambda 0 0 0, 4 minus 1 minus lambda 0 0, 8 9 minus lambda 0 minus lambda, this is minus lambda 0, so 10 11 12 3 minus lambda equal to 0. Now this is a lower triangular matrix, therefore its det is a product of diagonal elements. It is a lower triangular matrix, its det is a product of diagonal elements. My diagonal elements are this 2 minus lambda, minus 1 minus lambda, 3 minus lambda. So therefore this is 2 minus lambda into minus 1 minus lambda into minus lambda into 3 minus lambda equal to 0. This implies lambda 1 equal to 2, lambda 2 equal to minus 1, lambda 3 equal to 0. So lambda 4 equal to 3. Interestingly, when you observe all these 4 eigenvalues, 2 is its diagonal element and minus 1 is its diagonal element, 0 is its diagonal element and this 3 is the diagonal element. Therefore, when something is a lower triangular matrix, its eigenvalues are simply the diagonal elements. The same case is valid even for upper triangular matrix also. If something is an upper triangular matrix, its eigenvalues are simply its diagonal elements, right? Note this example. Second example. Note, if A is either upper triangular or a lower triangular matrix, if A is either upper triangular or a lower triangular matrix, then its eigenvalues are diagonal elements. I am repeating once again, if A is either upper triangular or a lower triangular matrix, then its eigenvalues are diagonal elements. Now we discuss few shortcuts on eigenvalues. Suppose A is a n cross n matrix. Since it is a n cross n matrix, it has exactly n eigenvalues. Assume that they are lambda 1, lambda 2, lambda 3 and so on, comma lambda n. Now the properties will be like this. Add all these eigenvalues, that must be trace of this matrix. So sum of eigenvalues lambda 1 plus lambda 2 plus lambda 3 plus and so on plus lambda n equal to trace of A. Trace means sum of diagonal elements of A, right? So sum of eigenvalues of A is nothing but trace of a matrix. Now replace plus by dot. So lambda 1 into lambda 2 into lambda 3 into and so on into lambda n equal to det A. So sum of eigenvalues equal to trace, product of eigenvalues equal to det A. Now these are eigenvalues of A. Now I want eigenvalues of A power k. So eigenvalues of A power k or lambda 1 power k, comma lambda 2 power k and so on lambda n power k. Just raise the powers of lambdas. So once these are eigenvalues of A, I can easily get the eigenvalues of A power k. Let me tell you one example. In the last example, for example 2 by 2 matrix, we got eigenvalues as 3 and minus 2. Suppose if you ask me eigenvalues of A power 16, A is some matrix. So in that case eigenvalues are 3 minus 2. If you ask me what are the eigenvalues of A power 16, just raise the power 16 for 3 as well as minus 2. So 3 power 16 minus 2 whole power 16. They will be eigenvalues of A power 16. You need not calculate A power 16. If you want to calculate A power 16, it takes a lot of multiplications. Unnecessarily we will be wasting our time. So this is not required. So if they ask you to find the eigenvalues of A power 20, just you get the eigenvalues of A. If they ask you to find what are the eigenvalues of A power 49, just you get the eigenvalues of A. Even if they ask you the eigenvalues of A inverse, just find the eigenvalues of A. Therefore, once you get the eigenvalues of A, you can easily get the eigenvalues of A power k. So simply what we are doing is we are replacing this A by lambda 1, lambda 2 and so on lambda n, keep the power k as it is. Now this is regarding powers. Now next I want eigenvalues of A inverse. That is, this is the particular case of this. So we are replacing k by minus 1. So the eigenvalues of A inverse are lambda 1 power minus 1. That is reciprocal 1 by lambda 1, 1 by lambda 2 and so on, comma 1 by lambda n. This is valid even for any integer. So in this case k is any integer. If you want what are the eigenvalues of A power minus 2, suppose when you take k equal to minus 2 in this case, that means we are concentrating on eigenvalues of A power minus 2. You can treat this as A inverse whole square. Now A inverse you can call it as some new matrix B square. So again it reaches to positive power. Therefore once you want eigenvalues of A power minus 2, get the eigenvalues of A and A inverse. Just raise the power 2, you will get the eigenvalues of A power minus 2. Therefore in point number 3, this k is any integer. K can be negative values, positive values, 0 also, but integer only, right? Suppose I want eigenvalues of multiples of A. So the eigenvalues of Ka or K lambda 1, comma K lambda 2 and so on K lambda n. In this case K is any constant. Fractional values will be allowed. K can be 1 by 2, 2 by 3, root 2, anything is valid. So in this case K is any real number. K is any real number. Therefore we got the eigenvalues of powers of A, we got the eigenvalues of multiples of A. But try to understand that what is the difference between point number 3 and point number 5. In point number 3, K is integer value only. Fractional value should not be allowed. So if you ask me what are the eigenvalues of A power 1 by 2, it doesn't make sense. If you ask me what are the eigenvalues of 1 by 2 into A, it makes some sense. So in case of point number 3, K is integer only. But in this case, K can be any constant. Therefore, I specified very clearly K is any real number. But in case of point number 3, K is an integer only. So K is an integer only. Therefore, these are the eigenvalues of A power K, eigenvalues of A inverse, eigenvalues of Ka. Next, I want eigenvalues of A plus or minus Ki. I want eigenvalues of A plus or minus Ki. Now this is a multiple of matrix. I is identity matrix. K is some constant. You can have either plus or minus. So this is identity matrix of size n cross n. Even it will be having exactly n eigenvalues. Therefore, its eigenvalues will be obtained like this. Replace A by first eigenvalue, lambda 1. If it is plus, write plus. If it is minus, write minus. K into eigenvalues of I are 1 only. Because when you take identity matrix, the diagonal elements are 1, rest of the elements are zeros. As we mentioned in earlier, if something is an upper triangular matrix or lower triangular matrix, my eigenvalues are 1 only. So interestingly, when you consider any identity matrix, its eigenvalues are 1 only. When you take 2 by 2 identity matrix 1 0 0 1, its eigenvalues are 1 1. If you take 3 by 3 identity matrix, its eigenvalues are 1 1 1 only. So all eigenvalues of identity matrix are 1 only. That repeats many times. Therefore, in this case, I is replaced by 1. Second eigenvalue is replace A by lambda 2 plus or minus K into 1 and so on, lambda n plus or minus K into 1. K into 1. So this is point number 6. So meanwhile, you note down these points. Next, I will go for the eigenvalues of adjoint of A. If A is a n cross n matrix, if A is a n cross n matrix with eigenvalues lambda 1, lambda 2 and so on lambda n, if A is a n cross n matrix with eigenvalues lambda 1, lambda 2 and so on lambda n, then continue up to point number 3 and I will dictate point number 6. Point number 6. The eigenvalues of A plus or minus Ki. The eigenvalues of A plus or minus Ki or lambda 1 plus or minus K into 1, comma lambda 2 plus or minus K into 1, comma and so on, comma lambda n plus or minus K into 1. The eigenvalues of A plus or minus Ki or lambda 1 plus or minus K into 1, comma lambda 2 plus or minus K into 1 and so on, comma lambda n plus or minus K into 1. Since all eigenvalues of I are 1 only. Since all eigenvalues of I are 1 only. Now, as a 7th point, let us find the eigenvalues of adjoint of A. Adjoint. Suppose when you replace A by lambda 1, lambda 2, lambda n, it doesn't make any sense. Adjoint of a single number, adjoint of single number, it doesn't make sense. Therefore, what we need to do is we need to convert this as a multiple of some matrix. As a multiple of some matrix. Suppose I have an expression like this: A inverse equal to 1 by det A into adjoint of A. Now from this, I can write adjoint of A like this: adjoint of A equal to det A into A inverse. Now this is in the form K into some matrix B, because the det is some constant, A inverse is some matrix. So in the earlier properties we mentioned the eigenvalues of multiples of matrix. So according to that we can easily get the values, but one restriction is here I have expressed adjoint of A in terms of A inverse. Therefore in this case I am putting one restriction on A, that is det A is not equal to 0. Det A is not equal to 0, because when det A is not equal to 0, then only A inverse exists. Then I can easily get the eigenvalues of adjoint of A. Suppose if you ask me to find the eigenvalues of a singular matrix, then this point does not work. If you ask me to find the eigenvalues of a singular matrix, that means where A inverse does not exist, then you need to go in the normal direction. So this rule does not work. So point number 7 is valid only when det A is not equal to 0, right? So because adjoint of A is expressed as a multiple of A inverse, because A inverse is this, from this adjoint is det A times A inverse. Now this is in the form multiple of some matrix, because det A is some constant, this is some matrix, so it is in the form constant into some matrix. Therefore I can easily get the eigenvalues of adjoint of A using this rule when det A is not equal to 0. Therefore according to this case my eigenvalues are, so det A is some constant, det A into the first eigenvalue of A inverse is 1 by lambda 1. So det A by lambda 1, comma det A by lambda 2, and so on, comma det A by lambda n. So all these n numbers are eigenvalues of adjoint of A if det A is not equal to 0. Note this point. Point number 7. The eigenvalues of ADJ of A. The eigenvalues of ADJ of A or det A by lambda 1, comma det A by lambda 2, comma and so on, comma det A by lambda n. Det A by lambda 1, comma det A by lambda 2, and so on, det A by lambda n. Because ADJ of A equal to det A into A inverse. Because ADJ of A equal to det A into A inverse, and det A not equal to 0, and det A not equal to 0. Hope you understand all these points. Now I will give some clarification on all these points. Just now we have discussed the 7 shortcuts to find the eigenvalues of general n cross n matrix. Let me recall those points wise. What is the point number 1? Sum of all eigenvalues equal to trace. Don't think that this is valid only for upper triangular or lower triangular. I did not put any restriction on point number 1, 2, etc. So whenever there is some restriction required, I have mentioned very clearly. Let me tell you what are the restrictions I have put on all these points. In point number 1, what it is? Sum of eigenvalues equal to trace of A. No restriction on A, whether A is a symmetric matrix or whether A is a diagonal matrix or scalar matrix or upper triangular or orthogonal matrix or skew symmetric, it doesn't matter. So sum of all eigenvalues equal to trace of that matrix. It is valid for all types of matrices, right? In the second point, product of eigenvalues equal to det. This is also valid for all types of matrices. Because when I discuss point number 1, why I am discussing all these points is, generally students may confuse about one point. As I mentioned earlier, what are the eigenvalues of lower triangular matrix? Diagonal elements. What are the eigenvalues of upper triangular matrix? Diagonal elements. So in that way, people think that lambda 1 plus lambda 2 equal to d1 plus d2, where d1 and d2 are diagonal elements of 2 by 2 matrix. So it works very clearly. So people may think that point number 1 is valid only for upper triangular or lower triangular. Certainly not. They are valid for all types of matrices. All types of matrices. So sum of eigenvalues is trace. Product of eigenvalues equal to det. The eigenvalues of a power k are lambda 1 power k, lambda 2 power k, and so on lambda n power k. There I have put one restriction. What it is? K is an integer value only. So k can be 2 or minus 2, 7 or minus 7. K can be 0 also. So all these values are integer values. Point number 5. Point number 4. The eigenvalues of A inverse. In place of k, we wrote particular value minus 1. So point 4 is particular case of point number 3. In point number 5, we explained the eigenvalues of multiples of A. So in that there is no restriction. K can be any real number. So k can be 2 by 3, minus 1 by 2, root 2, etc. All these are real numbers. No restrictions at all. Now in point number 6, we have got the eigenvalues of A plus or minus Ki. That is very simple. Just replace matrix A by its eigenvalues. Replace identity matrix by its eigenvalues 1. Now this is eigenvalues of adjoint of A. Right? Now let me make some comments on eigenvalues of singular matrices, etc. Now let us come to the point number 2. Now in point number 2, what it is? Product of eigenvalues equal to det. Suppose if det A equal to 0, suppose. So if det A equal to 0 implies lambda 1 into lambda 2 into and so on lambda n equal to 0. So product of n numbers equal to 0 implies at least one of these eigenvalues must be 0. Very basic point. When you multiply few numbers, if the outcome is 0, what does it mean? At least one of these values must be equal to 0. Implies at least one of lambda I equal to 0. So I may be 1 or 2 or etc. Therefore, that A is 0 means it is a singular matrix. That is, A is a singular matrix. Therefore, whenever you consider a singular matrix, at least it's one of its eigenvalues equal to 0. This is the most important consequence of property number 2. Now this, if A is a singular matrix, if A is a singular matrix, then at least one of its eigenvalues is equal to 0. If A is a singular matrix, then at least one of its eigenvalues is equal to 0. If A is a singular matrix, then at least one of its eigenvalues is equal to 0. Now based on this, we can easily tell about the eigenvalues of a non-singular matrix, that is whether it is 0 or non-zero. Suppose if det A not equal to 0. Suppose when det A is 0, this will happen. Suppose if this is a non-zero constant. Suppose if it is a non-zero constant. So when you multiply n numbers, the result is a non-zero number. That means no lambda equal to 0. That means when something is a non-singular matrix, no eigenvalue equal to 0. That means all eigenvalues are non-zero numbers. Hope you understand this point. Very basic point. Note this point also. Note, if A is a non-singular matrix, if A is a non-singular matrix, then all eigenvalues of A are non-zero. If A is a non-singular matrix, then all eigenvalues of A are non-zero. Then all eigenvalues of A are non-zero. Now based on this point, we will get one important point, that is a connection between rank of a square matrix and number of its non-zero eigenvalues. Very, very powerful point. As I mentioned just now, let us start with 2 by 2 matrix. If I have a 2 by 2 non-singular matrix, so all eigenvalues are not equal to 0. I have a 2 by 2 matrix. Assume that its det is non-zero. Therefore, 2 eigenvalues are not equal to 0. So if a 2 by 2 matrix is taken, if its det is not equal to 0, what is the rank of that matrix? It is 2. Since its rank is 2, the number of its non-zero eigenvalues are 2. Got it? Now let me generalize for larger dimensions. Suppose if A is a 3 by 3 matrix, assume that its rank is 2. That means 2 eigenvalues are non-zero numbers and rest of the eigenvalue is 0. Similarly, if I have a 10 by 10 matrix, if its rank is 7, 7 eigenvalues are non-zero and rest of the 3 eigenvalues are zeros. This is the most important point. This point is very powerful when you are solving many complicated questions. Suppose in the examination the question is given like this. The eigenvalues of the 4 by 4 matrix or options are given. So in that way, what you need to do is, if you find a trace of that matrix, assume that the trace of that matrix is 10. Assume that in the first option, when you add 4 numbers, the result is 10. When you add all 4 numbers in the second option, the result is 10. The same case is repeating for option C and option D, for example. Then by using trace property, we were unable to eliminate even a single option. Then in that case, you need to go for det of that matrix. For a 4 by 4 matrix, finding det is somehow not simple. But if you find, somehow if you are able to find its rank of the matrix, then based on that rank and property 1 and property 2, you can easily get the right answer. So it makes powerful sense to get the eigenvalues of a 4 by 4 matrix or anything. So let me recall this point. Now I am going to establish a relation between number of non-zero eigenvalues and rank of a square matrix A. So whenever A is a 10 cross 10 matrix, let me give one more example. Suppose A is a 10 cross 10 matrix whose rank is 5. That means 5 eigenvalues are non-zero numbers and 5 eigenvalues are zeros. 50% eigenvalues are 0, 50% are non-zero. So based on the options, you can easily get the result. Suppose if A is a 17 cross 17 matrix whose rank is 15. So 15 eigenvalues are non-zero and remaining 2 eigenvalues are 0. That means, let me generalize this. If A is a n cross n matrix whose rank is k, where k is less than or equal to n, then the number of non-zero eigenvalues equal to k. Number of non-zero eigenvalues equal to k. And remaining eigenvalues are zeros. So that is n minus k eigenvalues are zero. Note this point. If A is a n cross n matrix, with row of A equal to k, where k less than or equal to n, then A has k non-zero eigenvalues.